This video covers the intermediate value theorem. All right, so our first major theorem in calculus is going to be the intermediate value theorem. After we finish a couple of examples, we'll talk exactly about what it is, but the understanding of the intermediate value theorem is something that comes up on every AP exam, and it comes up in the form of a free response question, and where we generally have to justify an answer based upon understanding what the intermediate value theorem asks of us. So Mr. Martin came up with two different examples so we can see if the intermediate value theorem applies. In this first example, Mr. Martin knows someone named Christine, and she has a checking account. On the 14th of each month, she receives a paycheck, and the table shows her balance for a 13-day period. All right, so the first thing is, it's probably a 14-day period since it's day 1 through day 14. So I'm just gonna make that 14 instead. I just did some math and did 14 minus 1 is 13, but it's still 14 days. In this first column, we'll make this a function of t, and then we'll say this other thing is p of t, where t is the number of, we'll say seconds, nanoseconds. It's just t's time though. We can use anything that we want. T is going to be time, and P of t is going to equal account balance. Account balance. So the thing that we can understand is that t actually takes on every possible value from September 1st, my birthday, to September 14th. So we can say, we'll put in brackets, we'll say t assumes all possible values from 9/1 to 9/14. So if we're talking minutes, seconds, nanoseconds, milliseconds, hours, days, a week, whatever, it assumes all of the possible values from September 1st to September 14th. Can we say the same thing for the account balance? The question is, must there be a day when Christine's balance is exactly $3,000? Why or why not? You think about it for a moment, come back with an answer. All right, so I'm assuming you paused the video. If not, you should have paused the video. We will say this does, oh, okay, I didn't spell does right. So do does not have to be $3,000. Now the reason is this: money is a discrete value. It is not a continuous value. Let's learn some discrete means fixed values. So in America, we spend money down to the cent, and we don't go below that. So those are fixed values. I can have 1 cent, I can have 2 cents, but I can't have anything between 1 cent and 2 cents. Those are discrete values. A continuous value is it has infinite precision. So infinite precision if we want. Now we generally don't use continuous values because we only need to be so precise. So in the case of the first example, the answer is no. Christine's balance doesn't have to be exactly $3,000 because money is a discrete value. Money is a discrete value, meaning that she doesn't have to have exactly $3,000. She also doesn't have to have exactly $2,900 because you can skip that value by adding a certain amount of money, and it doesn't mean that you necessarily missed anything in between, which would make that function like a step function or something. In this second example, Mr. Martin's son, who turned 4 on Thursday, he's growing quite rapidly, and like many parents, Mr. Martin started tracking his son's height. So on the first day, every 2 months, I measured my son's height, and the table here represents his height for the following 6 months. You know what? But see, again, not 6 months. We're going to put a year because the table goes up for a year. So you can see that the height generally increases because kids generally grow and they don't get shorter. So the question here is that must there be a time between 0 months and 12 months? And again, we're not talking measured in months, that my son has to be, Mr. Martin Jr., that's his name, is exactly 100 centimeters tall. And tell me what you think about this. You think for a moment and come back. So the answer I came up with is yes. Growth in humans is a continuous value. It would be impossible for my son to go from 96.5 centimeters to 98.5 centimeters without being 96.51, 52, 53, 54, and so forth centimeters. He has to assume all of those values. Even if he only stays there for a fraction of time, he has to actually take on every possible height from 96.5 to 104.5. You can kind of think about it as walking somewhere too. You move in a continuous manner. Even if like you take steps, your body assumes all of the points in between your starting point and your destination. So the answer is, again, yes, because growth in humans is a continuous value. And so that leads us to the intermediate value theorem. The intermediate value theorem is, it says that a function that's continuous on a closed interval between 2 points f of a and f of b, it has to assume all of those values. So like we have this graph, we start at x equals a, we end at x equals b. And the intermediate value theorem says that if a starts here and b starts here, then you assume every value in between there. Like we have this point W, for instance. It's not possible to go from A to B without hitting W because we've assumed that f of x is a continuous function. So we hit all of those values. On the back, we'll just work some examples. We only have 2. So for this one, first determine if the intermediate value theorem applies on the given interval. If it does, find the value that find the value C that guarantees the value K. So K is the value, the output value that we want. Let's see, x squared minus 4x plus 1 on the interval 0 to 4. So to check this, we need to know what f of 0 is. F of 0 is equal to 0 squared minus 4 times 0 plus 1, which equals 1. Oh, you didn't see any of that. Let's start over. First, determine if the intermediate value theorem applies on a given interval. If it does, find the value C that guarantees the value K. My bad for that. So first we need to find f of 0. F of 0 is equal to 0 squared minus 4 times 0 plus 1, which equals 1. And then f of 4 is equal to, let's see, 4 squared is 16 minus 4 times 4, which is also 16, plus 1, which equals 1. So we know that f of 0 is 1, and we know that f of 4 is also 1. Does this function have to hit 3 at some point on this interval? We don't know. We know that the x values have to hit 3, but we don't know that the function values have to hit 3 because we start at 1 and end at 1. So what we're saying is this. Imagine you have a function that starts at x equals 1 and it ends at x equals 4, and all you know that is the function is continuous. So we know that when x is 1, the output is 1, and we know that when x is 4, we know that when x is 0, the output is 1. Start up. So here we know that when x is 0, the output is 1. And we know that when x is 4, the output is also 1. So there are a couple of things that can happen. It's entirely possible that we first have just a line that goes from 0 to x equals 4. It's also possible that we just have a function that does this and hits 4. It's possible that we have a function that does this and goes to 4. It's possible that, like, we'll call this 2, we'll call this 3. It's possible that we have a function that does this, that is continuous, that still doesn't hit 3. So knowing the endpoint values doesn't tell you anything if they're the same thing. There are too many graphs that you can draw that are continuous that go from 1 to 4 that don't have to hit x equals 3. So in this case, we would say the intermediate value theorem does not apply. So now, you know what? Let's do a second example. We'll do another example on just a scratch paper. We'll say we had the interval 1 to 5 instead. So we're going to use 1 to 5, and we still have the same function. F of x equals x squared minus 4x plus 1. The interval 0 to 5, and we're going to still see if we can get k equals 3. So now with x is 1, we get 1 minus 4. Well, 1 plus 1 is 2, minus 4 is negative 2. So f of 1 is negative 2, and then f of 5 is equal to 25 minus 20 is 5 plus 1 is 6. So on the interval 1 to 5, we go from negative 2 to 6. So the intermediate value theorem does apply on the interval 1 to 5, because to go from negative 2 to 6, k equals 3, we know this is a parabola, so we know it's continuous. So now we should find a value that the intermediate value theorem guarantees. So that means that we set this equal to 3, then solve for x. So we're going to have 3 equals x squared minus 4x plus 1. If we subtract 3 from both sides, we get 0 equals x squared minus 4x minus 2. I don't know about you. I'll just do the quadratic formula. We're going to have x equals 4 plus or minus the square root of, let's see, 16 minus 4 times negative 2 times 1. So 4 times negative 2 times 1 over just 2. So we get 4 plus or minus the square root of 16 minus 8. 16 plus 8 is 24. So the square root of 24 is the square root of 4 times, it is the square root of 4 times the square root of 6. So that's 2 square root 3, 2 square root 6, I'm sorry. And 2 divides into both of those, so we get x equals 2 plus or minus just the square root of 6. So 2 plus the square root of 6 is like 2 plus 2 point something, which is 4. And 2 minus the square root of 6 is outside of our interval 1 to 5. So we just want x equals 2 plus the square root of 6. And that's because we'll say x equals 2 plus the square root of 6 is in the interval 1 to 5. So we see an example where, so we contrived an example where the intermediate value theorem did not apply because we had the same endpoint value, and we just tweaked that to have an example where the intermediate value theorem did apply. So for this next example, we are finding, so we're doing 2 different k values. First, we're going to see if the intermediate value theorem says that there has to be some point for which p is equal to 0. And then second, if there's one where p has to equal 4. So let's see, p of negative 3 is equal to, I just use a calculator. Let's see, we can learn some calculator tricks. All right, so if you don't know this, I'm assuming you do at this point, we can do -3 stores as x. We press enter. And so we get that. And then we just type in our equation. We get 2x math. 3 is how we get the cube, plus 3x squared minus 5x. And we press enter. So p of -3 is -12. I want to show you another way that you can do this just so we can learn some more calculator tricks. Say we went to y equals, we'll clear this function out. We're going to do the same thing. We have 2x cubed plus 3x squared minus 5x. So another way to pull up the y value is you can press second table to get there. You know what? We can press plus, change by 1. So we go back to changing by whole numbers. And we want to know at -1 what the value is 6. So then p of -1 is equal to 6. So the question is, on the interval -3 to -1, is there a value for which k has to equal 0? Now, if you're given a calculator, the first thing you should do is just type this function in and look at the table and see what turns up. So on the interval -3 to -1, the answer is no, because we went -1 to 6, so -12 to 6. We see 2 zeros here, but we know since this is a cubic function and it's continuous that we have to hit from -12 to 6. Somewhere in there has to be a 0 from -12 to 6. So there are two ways to do this. If we have a calculator, the smartest thing to do is press, let's say we go to y equals, and we're going to graph this. All right, so right now my graph is not in the standard window. So what we want to do is press zoom and we press 6. It's going to take a minute to do whatever it does. Maybe it never graphs. All right, so we're going to press second off and we'll come back to this. All right, so we go to y equals, we're going to press zoom and we're going to do box. And so we want to make a box from, now it wants to draw. All right, so we want to restrict our function from -3 to -1. So we're going to press window, and we're going to go from, we'll say -4 to 0. And we'll leave everything else the same. It's going to draw. So the 0 that we want between -3 and -1 is this 0. So a way to tell our calculator to do this is we press second, calculate, and we just want to do 0. So when it says left boundary, we want to scroll somewhere slightly to the left of the x-axis crossing point, press enter, then move somewhere to the right. When it says right bound, move somewhere to the right of that crossing, press enter, and it's going to say guess, and then press enter again. It's going to give us -2.5. So for this, we will get for x equals -2.5. P of t, so for t equals -2.5, P of t is equal to 0. So that's one way to do this. Now, if we didn't have a calculator, what we'd have to do is set this equation equal to 0. So we get 0 equals 2t cubed plus 3t squared minus 5t. So the first rule of factoring is take out the greatest common factor. So we get 0 equals t times 2t squared plus 3t minus 5. And so then we would have t times the factors of 2t squared, and we'd have 2t and t. And so we're looking for factors of -5 that somehow can multiply with the 2 and the 1 and give us a 3. So I would say we have a -5. We'll have a 5 first. And so then because 5 is prime, we need a 1. So to get a +3, this 5 needs to be positive and the 1 needs to be negative. So we get a solution of either t equals 1, t equals 0. Or if we solve this one, we get t equals -5/2. So this is solvable by hand. I just wanted to show you a method for doing it on the calculator because that's going to come up when we do tons of stuff later on in calculus. So we'll save this other example for some other time because the video is running kind of long. If we wanted to look at the graph on the interval from -3 to -1, we can look at the table. And so between -12 between x equals -3 to -1, because the graph goes from -12 to 6, we know that there has to be a value where k that produces a k value of 4. So that concludes this video on the intermediate value theorem, which again says a continuous function assumes every value between f of a and f of b if the function is continuous again. So between a and b, it assumes all possible values. Thanks.